Hello and welcome to any of my combo lords joining me here, just in my room for now. I was hoping to do this live video out in the combo classroom, but it is drizzling, raining slightly out there right now. So hopefully, since the rain I think is short-lived and I'm going to check the weather over the next 10 or 20 minutes, we will be able to pay a visit outdoors to see some new things going on, maybe with our squirrels and birds and dice and such, since I mostly have finished filming the intro that will be our official intro to grade -2 coming on the main combo class channel in a few days. And although there were plenty of surprises already that have popped up in the classroom, such as the grandfather clock and other fun things, those aren't all of the surprises that I got for grade -2. Out of all the surprises that I got, I put about half of them sneak previewed in the finale very briefly and shown on this channel a bit, and the other half saved for our grade -2 official intro so that we can still have a little bit of surprising going on. In any case, we're going to start off in the room here anyways, because part of what we're doing today will be scrolling through some online pages using Wikipedia as an example of some fun tables and lists of various types of numbers that we'll encounter in the future. And part of this was just that as I was going to pull up one list of types of numbers on Wikipedia, which was when I was doing a short video on this channel pretty recently explaining to people who weren't sure yet the differences between a few types of numbers. For example, what does it mean to be an algebraic irrational number versus a transcendental irrational number? Things like that. But I didn't go nearly down all of the types of numbers. It was already a long enough video just going into a few of the most common types of what's called real numbers that live on the most common line we're used to numbers living on. And when I was pulling up a Wikipedia article of a reminder of some other similar videos I might do in the future. What are the other names of numbers out there that I may know a bit about but can't bring to mind instantly because there's plenty of fun types. I realized how many different articles Wikipedia has about different types of numbers. Just to scroll through, these are a few recommendations for anybody who likes my number theory videos to read through sometime. There's separately, we're going to take a look at a Wikipedia page for list of numbers, list of types of numbers, list of numeral systems, list of mathematical constants, list of integer sequences, tables of the divisors numbers have, tables of the prime factors numbers have, tables of what numbers look like in different common bases, ones specialized in types of prime number. And those are just the ones I pulled up real quickly that I remember having fun reading through at points in the past. These are a great use of Wikipedia because, you know, at its best, it's never really going to be the site that you, or the source that you use a citation from in your thesis paper. But it can point you in the right direction and give you a lot of data that you can, in math, often double check with your own common sense and seeing if it makes sense for the numbers to do that thing, as well as some trusting of other resources when you look up the ones that hook you. But we're going to scroll through just a couple of these today as jumping off points to discuss some other types of numbers that I made a long list in my head when I was making that little video recently about all the types of number I could have talked about, and I realized it would have been like a 1-hour video. And so I decided we're just going for the most common types of real number. But looking at list of types of number, we can see even in what they call main types, the ones that I covered here are basically these upper ones, plus I clarified the type called transcendental. And all of these are other sorts. I hinted at the imaginary and complex, and then you get to hypercomplex. And p-adic numbers are a whole different type of valuation of numbers that is a different way of measuring their size and their nearness to each other. What we'll look at for a moment right now, before we jump down off the deep end into these numbers, is a little explanation more about these types. What are the irrational, imaginary, complex, and hypercomplex? Because these were the closest to having gotten in that explainer video. I actually wrote them on the whiteboard, and then right before I filmed, I was like, wait, hold up to my camera guy. I got to erase these two. If I include irrational and imaginary, irrational is there. If I include imaginary and complex, this is going to be way too long of a video. Now, I already did somewhat of my intro to imaginary numbers on the main combo class channel in an episode about what's called the roots of unity. And I want to see if I can somehow find that clock I made about the roots of unity around here, but it might have snuck back outside. So I have this clock somewhere or another that shows these fellas called the roots of unity that are neat. But really the most important ones we can explain without the clock. The clock was for fun because if we go to the 12th roots of unity, it's incredibly clock-like. But when I say the roots of unity, it's sort of like the branch that gets you going down all of these paths, not to the hyper-complex. But the roots of unity are going up to complex. What are all the roots of the number 1? Which sounds sort of weird at first. You're like, well, the square root would be -1 or itself. The 4th root, at first, you might be like, well, the 4th root of the number 1 would still just be 1 or -1. Which it's true that those are 4th roots, but they're not the only ones. What happens if you raise the imaginary number I to the 4th power? Well, I times I times I times I. You got 4 i's multiplying. These two multiply to a -1. These two multiply to a -1. -1 times -1 is 1. So I to the 4th power is 1. In fact, it's true with -I too. If you take -I times -I, with 4 of them multiplied together, it's all the negatives cancel out and it all becomes 1. And so really you got 4 4th roots of the number 1, which sort of set up your classic start to how people learn the imaginary numbers. You got I, you got -I, you got -1, and you got 0. And if we look at the complex plane, that's the easiest way to visualize these, where you got a real axis and an imaginary axis, so that the point 1 would live around where they wrote A here. I would live somewhere around where they wrote B here. This point would be around the lines of 1 plus I. And the complex numbers really are the main exception to me saying that when you hear something in math, unless told otherwise, you assume you're on the real number line. That's mostly true that in a lot of branches of math and in a lot of arithmetic you'll ever have to do, if you hear a number, you assume you're on the real number line, unless you have a reason to think otherwise. But the closest to the exception of that is that there's a bunch of fields of math where you pretty much want to automatically consider them on the complex plane, whether you, quote, need to or not, because they give you more data that way. So there are times where if you hear a number, you might assume we're talking about this whole plane, which the real number is a line out of. But what about this one they called hypercomplex? Well, graphic designers are known to hate quaternions because they're like programmers of moving animations, because it turns out that these complex numbers are pretty good at describing 2D rotations. And so the level past that, you imagine, might be good at describing 3D rotations. And it is. It's called quaternions. Now, the problem, and the reason I've actually stalled on making an episode about this is I have in the back of my head that'll take a really long distance field trip in one of these grades to the actual bridge in a different country than me, where the guy originally discovered quaternions and carved on the bridge, apparently, which there's no plaque there. I don't think they have the original carving. But apparently, the guy carved on the bridge his revelation about how to make the quaternion system work. And basically, I'll explain this a lot more when I make an episode, but the cool sort of twist that he had to come to in general to go to these quaternions, and then this next one called the octonions, well, we're used to I in the imaginary numbers adding a second variable. Like you have an amount of ones now and an amount of I's. So they wanted one with 3 variables that worked well, and he could not find one. And it has been proven that for the properties he wanted to make it the next logical extension to the complex numbers, you need 4 letters. You have 1's, I's, J's, and K's. And you do lose some properties that the complex numbers maintained. As you go deeper into these, you start to lose properties like commutativity and associativity, for those who know what those are. We'll explain more about those as we go on. So these are not as steady or stable as systems as the complex numbers in some ways. They're pretty neat, but due to all these tables that you have to memorize about how the I's and J's and K's interact, a lot of people are a little bitter that the quaternions got busted out and turned out to have some importance to study in some fields. They're like, we just learned imaginary numbers. What do you mean there's 2 more variables? So I'm going to take a peek at the comments for a minute. Thank you all for joining me here. And someone's saying that no matter the type of numbers, they all lay on a line going from minus infinity to plus infinity. That's more just the real numbers you're referring to there. You may have commented that before I started doing this stuff, but the complex numbers, one of the whole points of them is that they add a dimension. And so we do have a number line, but the complex numbers are very accurate to describe as a number plane, a 2-dimensional field of numbers. And that's why it's super neat to me, I made an episode about base 2i and also bases like I minus 1 and stuff. These bases are super cool because with a finite length string of symbols, they can convey a whole field of what's called the Gaussian integers, the grid points on this plane, instead of like the notched marks on a line. And so, although we see numbers as on a line, and many systems see them that way, part of what's going on in these hypercomplex ones is that we're gaining dimensions. We're going more dimensions outward, sort of. Makes them harder to visualize because since complex numbers take 2 axes to describe a single point, if you want to graph, here's my inputs and here's my outputs, you'd need the way that we see, like I graphed a parabola. Here's the inputs of x to the output of y. Well, if I want to do that with complex numbers, we need to figure out workarounds because otherwise we'd need 4 axes, 2 for the input and 2 for the output. And we can't visualize 4 axes that easy. So sometimes you have to compare just the absolute value magnitude of the numbers on one axis, or sometimes you need to have multiple going next to each other or show the movement through time or stuff. So it does get harder to visualize at this point for sure, because with an input and output, it's already past what we can just geometrically make a graph of that a human can understand. But back in the history of math, geometry used to be like the boss. The final boss was geometry. All other branches of math bowed down to it. If geometry said something didn't work, the other branches would be like, fine, I'll stop trying it. But then people learned after a while that we were getting limited by seeing things as distances instead of a number as a symbol, and limited by trying to geometricize or whatever things that only let us see up to the third dimension easily, because that's how our brain and reality works. It's like a 3D thing. How do I visualize fourth powers? Well, fourth powers aren't that much weirder than third powers, but they're way harder to visualize geometrically for us, because a third power we can describe as a cube. And we need to bust out the hypercubes to describe a fourth power. So fourth powers could be called the hypercube numbers, you know, or the 4D cube numbers, but they're harder to visualize. So over time, math started to bow down a little more to algebra, and then it started to bow down even further toward these vaguer ones like category theory and group theory and ring theory, and the ones that sort of like define what's going on and really look at like, why did we set up the system the way we did? What rules were we following? What did we get out of that? What if we had followed other rules? What would we gain or lose? Someone's asking if this is live or recorded. It is live. But to those who leave comments because they want me to answer the comment, I will get to them at some point, but you may have to stick around for a minute. So yeah, we got a lot of night owls in Asia, it seems. A lot of people saying they're in Asia in the middle of their night. We got combo lords, as I call our viewers here, from all over. Pretty cool. Here for me, it's the opposite time. It's about to be 1 in the afternoon. So time's all over. Wild. That's why I try and make these streams be digestible to watch after the fact, if you ever have time to watch a long video, so that people in other time zones can still catch them. This month's predictable live stream schedule, by the way, I mentioned this once or twice, but it's going to be every Monday at my 6 p.m., which is 6 p.m. Pacific time. I will for sure be live on all of the Mondays, doing one called Modular Mondays. Then there will be other random ones throughout the week like this. Pretty soon, I will shift back focus a little more to my other combo class channel. So there may be a mild shift in how much is coming out there versus coming out here, because that is where I put my better, more finished projects. And I have a lot of topics that I don't feel like I'm going to do them justice in a long one-take video on this channel. A lot of the videos on this channel are just one take without editing, apart from maybe trimming the ends. And so a lot of the ideas, I'm like, well, I gotta finally just make a full episode about this because I've been brainstorming it a while. So there'll be a lot of fun math episodes coming out on that main combo class channel. Plus, I'm going to start putting maybe some of my shorts on there, because the shorts were so good at showing people this channel that I might put a few of my shorts on that channel too, just to show the shorts algorithm people that channel exists. And the first episode of Grade -2, though, which is coming out in just a few days, probably sometime between Sunday and Wednesday, the first episode then is just a kind of silly intro. Very fun, but it's just going to be like 5 minutes of mostly classroom gags. Tiny bit of math. Then we're going to jump right into the math lessons the following week. This channel really is my less perfectionist channel. It just happens to be the one with all the viewers because I do more stuff on here and because it includes the shorts. So someone's wondering, why are there a lot of Greek words in math if we can visualize alphabetical letters more? Sometimes we use the letters of like what looks like the English language or other letters like that to mean things. Like the letter E is a number, X and Y and Z are really common variables, A, B, and C are pretty oftenly used as variable names as well. N sometimes is a variable when you want to specify that it's a certain type of number, like sometimes they use N to mean a whole number or a rational number. Sometimes N versus M will be comparisons. P and Q are sometimes used for two different primes. So we do use the letters for stuff, but some of them are unused. But I think we mostly save those for variables. If you see an English letter that's like not E, you usually assume, okay, I'm working with, this is supposed to represent a variable, like X does. And there are plenty of Greek ones. The weird thing is when we double up on one, like Sometimes they use a pi symbol to mean a product. Sometimes there's a lot of doubled up ones that get confusing. So that I agree with. If we have ones that are meaning two things at the same time, there's enough languages of symbols to pick one. In fact, I've been saying it's pretty silly that with all the symbols that exist out there in the English system, that like the 10 digits and 26 letters we use here in America and various English speaking areas, those it's ridiculous that with all the symbols possible, we made 0 and 0 look so similar, 6 and 9 be upside down versions of each other, I, L, and 1 all look similar. Just plus, X, times, all of these look like the same thing, sometimes rotated. Ridiculous. So there's enough symbols, we didn't have to double up on all those. So, thank you all for joining me. To jump back into this for a moment, before we maybe see if the classroom is possible to visit, if the drizzling rain has stopped, which I gotta be cautious when I'm out there anyway, because there's trees above it, and when it rains, there's raindrops in the trees, like dropping just one at a time every once in a while. So, gotta be cautious when I'm out there, but, you know. Things are made to be used. So here we got more types of number. Now the p-adic numbers, I'm not going to go into them now because they definitely will get their whole episode sometime. They're really cool. They're like my little sneak preview of something that is similar to their idea is, well, we might say like 27 and 28 are close because they're 1 apart. But prime factorization wise, in terms of the multiplicative structure of them, they're very different. Like 27 is 3 cubed, 28 is a pair of 2's times a 7. So does 27 actually have more in common with 28 or with 54, which is twice 27, and does include that 3 cubed within it? Maybe we could say if my metric is how pure threeven it is, well, those numbers are closer in pure threvenness. Pure threeven meaning like powers of 3, how many threvens in the prime signature. And if we add how threeveny a number is in terms of the exponents, then we would be sort of comparing a different type of closeness numbers could have. And so they made a whole valuation on like a more formalized version of stuff like that, about when we look at numbers, a totally different way of writing them, where they can be, for example, infinite on the left side of a decimal point. Like we're used to numbers can be infinite on the right side, but we're not used to you could make one infinite on the left side. So it's a very different way of viewing numbers. It's not just a base, it's a different system. And basically the hypercomplex, like I said, are basically just going past complex layers out. We will do those too at some point. So to those who still don't understand imaginary that much, maybe see at some point my Roots of Unity episode. Here we get some classics. Here you get what are numeral systems. They got a sublink to that other article I already had pulled up, which this, I guess, is going to be a longer version of this. And, you know, Wikipedia is full of great data. Look at all these different types of systems that have existed in the past. Now, we've discussed ones like this. These are what I call the basic bases. They call them standard positional numeral systems. And standard is very vague, so I clarified what I mean by basic base in my videos. Is basically what they take for granted is like, okay, it's any integer is allowed for the base, and it's an integer 2 or greater. To follow the same rules of the digits you use range from 0 to 1 less than the base. Each spot in the number follows the exact same like rules for what powers of what number part of the base it is. So a lot of those people take for granted when they're like another base. I'm calling those a basic base so we can be clear. And you could just go forever. You could keep naming them, you know. Some of the best ones are base 2, base 3, base 6, base 12, base 24 and 30 aren't bad. So here you get your less standard, and here you get bijective base 1. Thank you, Wikipedia, for clarifying that tally marks are not one of these. Tally marks are not a standard positional numeral system. If you followed the same rules, they would only use the digit 0 and get nowhere. They are an example of bijective base 1, which starts from 1 instead of 0. It goes from 1 through n in that case. And here you get your other bijective bases. They listed the one that lines up with our base, and here it looks like they listed the one that lines up with the English alphabet, 26. Otherwise, it would be quite random to pick that one. Still quite random. So now you get signed digits. We are going to do the one that they have an article about here, balanced ternary. Balanced ternary, I've mentioned, is where you have 3 types of digit, but it's not 0, 1, and 2. It's 0, 1, and -1. And it's sort of like how in mods, like in mod 3, I could say things are congruent to 0, to 1, or to the thing that we could either call 2, or we could call -1 in a way. And it's even the kind of closer to the nickname I gave that type of non-Threeven number. I called them pre-Threeven throds as opposed to doubly post-Threeven throds, because it's an easier nickname to think of them as the one before the next Threeven instead of 2 after the last Threeven. So balanced ternary, we're actually going to do some fun weighing puzzles. Like some little riddles about weighing that secretly are related to balanced ternary. And check it out, computers. In fact, to give that episode a catchy title, we'll probably have something in the title about how it is a base that certain computers use instead of binary. Here you get your negative bases, and we did cover these. We covered like -2 and -10, but the rules are the same for these. Gotta love those negative bases. People love those episodes on the main channel, so maybe I'll have to do the balanced ternary one pretty soon. Complex bases, and yes, we didn't do all of these, but we did 2i, and we did -1 plus or minus I. So all of these ones are on the main combo class channel, so make sure you've seen those after the stream, even though I'm assuming the people who watch my streams have, because those are like some of the more viewed videos on there. Non-integer bases, more classics. We've covered some like base 3/2, the square root and cube root bases, and the golden ratio base. We also covered how these ones are not that practical, like base pi. And we did not go into this yet, but we will. There's ways in which base E minimizes certain things, but it actually makes base 3 minimize things in a more practical way, because base E is not that functional and 3 is the closest. And here are basically the p-adic numbers of listing various types like that. Dyadic, for example, are the 2-adic numbers. Here we got other cool ones. These will at some point be episodes. The mixed here means that the different positions, it is positional in that different spots in a representation are different amounts. Like 2, 1 is going to add up to different than 1, 2. But, except in some of these maybe, but in most of them. And definitely, typically, that will be the case. Otherwise, you wouldn't call it even a positional system if all of them are the same, like tally marks. But in these positional ones that are mixed, the positions are not just powers of a base. It follows a less standard rule, such as each spot is a factorial. The problem with that is some of these require up to an infinite amount of digit symbols. If you wanted to really be able to describe any symbol of number, you'd have to come up with arbitrarily many digit symbols for some of these. The bases we use that I call the basic ones are actually really cool in that the way powers of numbers happen to work is that for whatever power of an integer you pick, you can just use that many digits, which we usually go 0 through the 1 less, but that many different symbols. So, that needs 5 symbols counting the 0. That needs 7 symbols. So they happen to work really neatly like that. It's not like automatic that if I make up an idea for a base, that it would not necessarily need an infinite or arbitrarily large amount of symbols. Still, despite that, some of these are used up to a certain size, and you just have to be ready to, whip out a new digit symbol if you're going to get too big. And there are non-positional ones, such as Roman numerals. Positions matter, but they're a completely different type of positions. Roman numerals are funny. We'll do some history of those someday. Their main downfall was they didn't have a symbol for 0. Not having a symbol for 0, is really going to hurt you. It's also another type of base that would, not base, but system that would need up to an infinite amount of digits if you really wanted to describe all of the integers. So, a lot of cool things here. They have like a whole nother article on list of numeral system topics. I don't know how much overlap there is there. But then you got whole other types of thing. Like those are just the numeral systems. Here we got what are types of integer. These are number representations for a reason, because this is not really telling me traits about the number. It's telling me, here's a system to write numbers. And so these are base independent traits, for example. No matter what base I'm in, which, as I'm mentioning before, we are assuming at this point, when we say types of integer, unless we're told otherwise, that we are on the real number line. If we do here, we could be talking about Gaussian integers, but we'll specify if that's the case. Here, the fact that they just say integer sort of lets us know we're just talking about the real number line. The way of describing it is sometimes surprisingly casual, where like up here it's just like main types, and some people might think that's too casual, but it's like, what do you want them to say? You want them to pretend that there's some rule for what it means to be a number system or not? They're just like, nope, it's a sliding scale, and these ones are the main types. These are the most useful so far to investigate. So these are fun now here because it's a whole separate realm, not like, ooh, with a system of digits, can I represent stuff? Now it's like, okay, the stuff I'm representing, what are traits it has? Even in odd numbers, prime numbers, composite numbers, and these ones that we are going to do multiple episodes about in grade -2. I've been working with an animator to throw in some cool animations in the middle of an episode of polygonal and polyhedral numbers, which in general are categories of what's called figurate numbers, numbers that can be represented in a geometric way, but then it's a geometric sort of sequence that you're counting the amount of something in it, and that gives you an integer sequence. So the polygonal numbers, for example, include the square numbers. We take for granted often that square really means square, but if you make a square amount of dots and count them, it's a square number. And so the triangular numbers are super underrated. These are awesome. We are going to make these more popular over the course of grade -2 because they're going to show up in a bunch of episodes and I love them. And people give the square numbers so much credit, they forget that they're along with triangular, pentagonal, and other types. So for sure there will be an episode in the near future called something like the polygonal numbers apart from square numbers. and the integer sequences, which brings us to this other page that I had open, which is look at all these integer sequences. Now, the thing is, this isn't going to be the best resource for integer sequences. This thing called the OEIS, the Online Encyclopedia of Integer Sequences. I've been there on some streams in the past, and it's a great website, one of the greatest of all time. But here, they're just trying to make it a little neater because the OEIS, as much as it's like one of the greatest websites of all time, in my opinion, it's a little hard to navigate sometimes. Like, they have some really cool sequences that can be hard to find if you don't know exactly what terms to search. They even have Wikipedia-like sections that are really good write-ups about concepts that are kind of buried on there. So it's a little hard to find all the good stuff on there. So here is a slightly neater version of a lot of the classics. And they do have the OEIS thing on the side. So say I wanted to know more about Euler's totient function, which will be in several episodes this grade. I know I've said that about a few things, but I'm only saying that about the things that I actually think are going to be in a few different episodes because they keep showing up. This thing keeps showing up. It already showed up, even though I didn't name it as such, but there was an episode about spiky shapes on clocks, and the spiky shapes, if you tracked out going 4 dots, then 4 dots, then 4 dots, or whatever, the ones that touched every corner was when the amount I was hopping was co-prime with the amount of dots on the circle. And since we were in modular arithmetic clockland, where 13 equals 1, we only had to consider the ones up through our clock number, like 12 in the case of a lot of clocks. And so technically, this is exactly what we were looking at. I didn't name it this because I was already throwing a bunch of new terms like co-prime out in that episode, and I wanted to make a separate episode focusing on what this has to do with these things called fairy sequences. But we did look briefly at this trait, the number of positive integers less than something that are co-prime with it. What does co-prime mean? Doesn't have any factors in common with it apart from 1. So like here they're saying that 1, 2, 3, 4, 5, 6. 6 only has 2 positive integers smaller than it, or not greater than it, but it's not going to be co-prime with itself. So they might as well say smaller than that. Well, here it's a nicer definition. They show how wide the bound is, but it's not going to include itself. So it's the same as saying smaller than. That don't have any factors in common, bigger than 1. Those numbers smaller than 6 are 1 and 5. Like 2 and 4 have a factor of 2 in common, and 3 has a factor of 3 in common with 6. On the number 12, for example, it's 1, 5, 7, and 11. And it turns out those are the numbers up to 12 that if I have an alarm ring every that many hours, I will end up touching every of the 12 times. Because that's the spiky shapes episode I made explains that. The thing is, this is going to come back. And the funny thing is, the exact clock animation that the Magic Fellow, my main Discord mod, helped me with, the animation I used in there is going to come back in a music theory lesson. Sounds completely random, but the idea that 5 and 7 are some of the numbers that when you have a clock with 12 numbers ring and you ring every 5 or 7 hours, your alarm will eventually go every hour number out of the 12. That relates to the 12-note scale we use in music and why it settled on being a functional thing. So we will actually be comparing Euler's totient function to music theory. But I was just using that as an example of if I wanted to know more about it, like the OEIS right here. Oh man, you can see how fundamental this thing is. It has the 10th entry on the OEIS. Obviously, the lower isn't just the more important. It was just early ones they were putting in. Like, this isn't necessarily the second most important sequence, but like the prime numbers aren't until 40th. But still, the fact that this was the 10th one they input on there says a lot. So here you have the totient function. Once again, this is what I was saying. They reuse stuff too much. This little phi there is, which the funny thing is, it is more technically pronounced phi, but then pi, would be technically more pronounced p. I don't think we want to start calling it p. So I have been calling this one phi because that's more correct on the Greek thing, but we don't do it correct for the other one. So now I'm second guessing my correctness on this. So in any case, we can make a list right here. These are the nth term and n. We can, if we want a longer list, go down and somebody's going to have made a really long list of all these values. These are traits about it that people noted. So this website's great. So this Wikipedia thing is really just about putting these in a neater place. Let me take a peek at the comments again, because it's been a moment. And then perhaps we will see if we can take a little visit outside. Let me see if it looks like it's raining back there. One sec. Is raining the smallest, mildest amount, but still probably bad for the computer. So we might have to pause on outdoors for now. Don't worry if I don't have time to do a live stream out there in the next day or two. In a few days, there will be a super fun grade -2 welcome episode on the main combo class channel. Also make sure that you've all checked out the long documentary-like and just chaotic adventure-like finale episode that I put out on the main combo class channel, which tells you a lot of crazy unseen things from my life, as well as some fun adventures. So, taking a peek at our comments for a moment. Welcome to everybody, and thank you for joining me. And let's see. Somebody asked what I think about the way numbers are defined. Well, numbers are defined a lot of ways. If you mean, like I was saying, we often assume we're on the real number line or the complex numbers. What do I think of those? I think they work pretty well. I think that they are pretty well functioning systems. And they help us visualize a lot of stuff, as well as, abstraction. But I do think that we shouldn't get too hooked on the ways numbers are defined. For example, I don't necessarily like the base we count in that superbly. The base 10 system isn't necessarily the ideal. In fact, it's not the ideal. But so things like that, we should always be willing to change and upgrade them. The way that we have numbers defined right now usually is pretty functional, but we shouldn't, hesitate to test alternatives. Someone's mentioning that the first published calculation about complex numbers was from the mathematician Cardano, which I definitely believe because I have read things in the past about his innovations and that type of thing. And some more good definitions of what happens to these. Let's see. And I think someone else is answering the parallax question. So we're going to do a little more looking at these for a moment. And then right at the end of the stream, we'll see if there's one last chance to visit outside, but might not be in this stream. So here what we have is a fun suggestion for you folks to go through if you enjoy my videos. Whenever you're bored, look through here, because you can tell the blue ones all have their own article too, for any of them you find interesting. Some of these are things we've discussed too. Like definitely discuss the prime numbers and Fibonacci numbers and powers of 2. and various ones. There will be some that will show up in the future, will include polyomino, and a lot of these will show up in the future. I just mean ones that will more likely show up in the next grade or two. The polyominoes, the Catalan numbers. We already mentioned the lazy caterer sequence and the factorials. The sum of proper divisors will for sure come up. Primorials will get a little more focus. These fellas you gotta love. These are also arguably a type of figurate number along with the triangular and squares. Oh, there's a lot of these. Okay, I can't list all the ones that are going to come up. A lot of are going to, tons of are going to come up. Some already have, such as the weird numbers and a lot of ones. Prime knots, we haven't done that. Oh yeah, but that's pretty neat. The number of prime, not meaning prime number, meaning a prime knot, a whole different thing. The building blocks of knots. So that's a pretty neat one, and mathematicians don't know that many terms in this. I think that we, looks like we only know up to about 19, if these last ones are even definitely correct, which I guess they are. Yeah, only up through 19 so far, it looks like, unless the next ones we probably have some of the prime knots, but might not necessarily know it's all of them. So that's neat. Now, the other cool ones that I wanted to mention on here are ones that I've sometimes pulled up in streams to have useful traits of, but they're very interesting to read through sometime on your own also. What traits do these first numbers have? And I kind of wish they merged these two in a way into one page, but we can flip back and forth and see some of the really big traits numbers can have. Like these are the divisors, it's how many divisors, it's what the divisors add up to, this is what the divisors apart from itself add up to. Here are its prime factors. And this gives you a lot of data about it. These ones even have notes about some of the traits that are defined in terms of their divisors or in terms of these sums, like all these things 6s, or the ironic fact that 2 is prime but is highly composite. It's not composite, but it is highly composite. It's also deficient, which means it's not abundant, but it's highly abundant. So 2 is two types of number that is the highly version of, but not the normal version of. This one, it's even the superior highly version of, but not the normal version of. So those names get funny with the small numbers because it does fit the definition of what highly these things means, even though it's not the thing itself. So that's a very useful list, as well as table of prime factors, and table of bases, table of representations numbers have in different bases. And here's another one that lists the first prime numbers, and then they list some different prime types. These are fun to read through. What are different specific types of primes that are named by mathematicians? For example, they'll definitely have Mersenne primes here. We've done some talking about these Mersenne primes. Binary hyper-11s. They look like a string of ones in binary. And they include the largest primes known to humanity. And there's other types of primes. We're going to go into the Fermat primes at some point, because those have to do with which shapes are constructible. And we're not sure if there could be, theoretically, an infinite amount of them, or just these 5. Or somewhere between. Most mathematicians do think it's just those 5. Now, a lot of fun ones. You got your palindromic primes we've talked about, and all sorts of cool ones. Part of what I wanted to do in this stream was show a variety of my favorite number theory list-like articles on Wikipedia, for anybody who's bored and wants to study on their own this weekend or this year. Now, you can also try and go to like any of these numbers and see what's up with it. Like, what's up with the number that looks like it's all fives in our base? Oh no, they don't have that one, do they? They're just primes, yeah. So in the primes, what's up with 4111? Well, turns out it's not on here. So the game doesn't work with numbers of this size. They shouldn't have made that blue. Why'd they make it blue if it doesn't have a link? Come on, Wikipedia. Now, if you go to a small enough number, my game works. So you're like, what's up with 61? 61 has all these traits. So I think Wikipedia for math's a little underrated. It's kind of sloppy. It's not perfect. Once or twice I've seen a wrong thing on it, but I've not seen very frequently a wrong thing on it. And as long as you follow up with checking any data it tells you on another site, if it's going to be important data in your life, then it's a great jumping off point. It's also a little bit maze-like and choose your own adventure-like. You get to go down the little rabbit hole of, oh, now I want to see Goldbach conjecture. Now I want to see natural number. Now I want to see this. And let's see what else we got going on. Somebody's mentioning possible difficulties of our math system interacting with aliens and their own possible math systems. And I think that if we wanted to help our ability in the future to communicate with any aliens, it would be good to get more comfortable with the different types of numbers and the different representations numbers could have, because it's very likely that if there was some sort of alien that did math, it's not guaranteed, but it seems possible at least. So I don't know about likely, but at least quite possible that they would have ended up having some use for a system involving integers. Maybe they would have ended up finding similar field properties that we found to what the integers have. And there's other ways you could imagine them observing math, like they're a dimension higher or lower, or they only see things continuously instead of discrete, or various ways. But I can imagine if there was 10 alien species that all separately came across math, there's, depending what we define as that they do math, then I would say maybe one of them at least would have had some systems not too far from ours, but it would be very unlikely that they would have base 10 the same way we do. That's dependent on so many things. That's dependent on, you want to have a positional representation with a finite amount of symbols, but to try and represent an infinite amount of things, and you want to have it be powers of the base, and you're going to have the whole number part on this side and a fractional part on this side, and you're going to separate them with a dot-like thing, and you're going to use digits that range from this to this, and you're going to, all of that, is less likely. In fact, I like to think that aliens would be a little smarter than humans and would have based what they count on not just on the historical fact that they counted on their fingers sometimes and how many fingers they happen to have if they had those, but on a more logical base number. And as we'll go into over time in combo class, this is a long, slow thing that we'll continue to learn about. The ideal base, in my opinion, for humans is base 6. So we'll go more and more into that over time, but just as one example for how that's actually just a similar, better version to base 10 is 6 and 10 are the first two semi-primes. Their factors are two different primes multiplied together. And they're, well, the first two square-free semi-primes, because you could say 4 is technically a semi-prime by being two 2's multiplied. But 6 and 10 are the first square-free semi-primes. And if you're going to have your base around those, it has particular traits. Like, there's a certain amount of factors for the number that looks like 1, 0, 0. If your number is a square-free semi-prime for your base, the number that looks like 1, 0, 0 is going to have, let me see. 9 factors. And that's true, that 100 in our base, the number 100, has 9 factors. 100 in base 6, which means the number 36, also has 9 factors. So you get a lot of traits similar for like this representation is this powerful. And base 6 gets it earlier and smaller. Like, people complain about the fact that, like, we would sometimes need 1 extra digit to write things if you had a base like that. But that's barely going to be annoying when you think about we mostly use smaller numbers, and now like the main symbols, things like 100, will be referring to more tangible common things that are equally powerful as the bigger 100s that our base has. So you could even take that game further, and the number that looks like 1000, the number that looks like 1000 in any square-free semi-prime base will have 16 factors. I'm calculating that based on the stuff that I did in my episode about prime signatures. And it's just like more functional to have that come earlier, to have you quicker in your number line be having the highly divisible numbers, the ones that you're using. So there's even, I'm going to mention this at some point, of the gap. I'll make an episode of some sort explaining this. As you get bigger and bigger, the gap between how many factors 1000 has and similar numbers of that size have, the gap gets bigger and bigger. Like if you compared the number with the same amount of, the smallest number with the same amount of factors as 1000, then that would be a tiny number, because 1000 is not actually that divisible. And even if you said in a square-free semi-prime base, well, at that point, instead of going from 36 being as divisible as 100, we're at the next power, which is 216, is just as divisible as 1000. It's not the smallest first one, but it's the example that the square-free semi-prime base would generate. So basically, the gap between certain things gets bigger and bigger, but the ones we're using on the higher end of the gap, it's not good for them to be big because they're not getting anything by that being our big landmark that the smaller ones aren't. I'll explain that better in the future over time, and a lot of these roads lead to that because I came to the conclusion that base 6 was the best, partially through like researching all the episodes that I've been making and that I'm going to be making, and continually finding important traits about even numbers, threeven numbers, multiples of 6, which are the even threevens or the threeven evens, and stuff like that. And so we're going to have tons of episode topics where it's just like, yep, here's another important thing that threeven numbers are doing. And our base is worse with threevens, but better with fivens or fivens or whatever, multiples of 5. And there's not going to be as many episodes where we find something marvelously cool about multiples of 5 or powers of 5. It'll come up. There will be really cool things occasionally about powers and multiples of 5, but way less frequently than powers and multiples of 3. Imagine how common evens, odds, and powers of 2 are to the powers of 5, and just know that the threevens are way closer to the importance and commonness of the powers of 2 than to the 5. And so over the course of this grade, we will learn more about those, and all of my stuff about how threeven should be in the dictionary goes hand in hand with my stuff about how base 6 is better. And there are also even our other ways to count on our fingers. Let's remember, we could have used the thumb. That's our opposable different thumb as a pointing device and counted 1, 2, 3, 4, 5, 6, 7, 8, 9, or stuff like that. Most of our fingers are divided into 3 joints. the 5 is like kind of random. We have like 4 fingers, 1 thumb that you can call 5 fingers casually or 5 digits, but it's sort of different things. It's like this is the opposable thumb that made humans be able to develop tools and fire and become this dominant species on Earth. And these are more common other little appendage little things. And so I could equally logically have seen us call it 8 or call it 2 or, you know. So we're not stuck on 10 being the notable thing going on. Someone said you saw a conclusion that base 11 would be good at teaching multiplication. I don't know about that. I mean, base 11 would maybe be useful as an example, because it might be like if you already know how to do base 10, base 11 could be a good mild stretch to here's a whole different way numbers can work, but we're only adding 1 digit for now. So it would be a good like early extension to what bases mean. But base 11 is a prime base, and while there are some things that are good about having prime bases, overall it's more important to have a divisible base than a prime base. So like in that base, you'd have every single fraction pretty much would end up needing a repeating decimal. And so, like, not literally every single thing you could generate something that didn't, but if you look at like in base 11, like 1/10 is going to need a repeating decimal, 1/3, 1/2, 1/5, those would all need a repeating decimal. So it's not the best base to do a prime. There are cool things about primes in... I talk about modular arithmetic a lot, which works similar to the last digits of bases and works similar to clocks. And there are cool things about prime mods that let you do some neat things. And we will see that at play when I show modular division. But until that episode, overall in general, a base that's a prime would not be ideal. It would actually make things a lot harder. If anything, that would just be good to like show someone as an example. And for anyone who says to teach multiplication from a base, if you actually look at the tables, base 6 is the neatest. Like, you can look through all of the multiplication tables. In my opinion, base 6 is the cleanest, neatest patterns. This is assuming you learned any from scratch, because if you like, well, what's the easiest when you already know base 10? That's a very different question than what's the easiest to teach someone for the first time. But to teach someone for the first time, if we weren't already stuck on base 10, the multiplication tables in base 6 are far easier and simpler. And that's because all the numbers going up to 6 or above that, you have 1, a factor of 6, a factor of 6, a number that shares a factor with 6, the number 1 less than 6, 6 itself, 1 more than 6, number that shares a factor, number that shares a factor, number that shares a factor. So it's really easy to express and multiply stuff in base 6 compared to other things. With base 10, you got 1, shares factor, doesn't, shares but partially, doesn't, shares doesn't itself, the next one. So you have, and I guess the dozen at the top, the 9, we could say it's 1 less than it because I gave that credit to the base 6, but still there's far more that are going to be harder to multiply in base 10 or divide or express as fractions as decimals and stuff because of having less factors in common. And to whoever's noting stuff about powers of 2 and powers of 5 that are close to each other, that is very interesting, but what I mostly meant about when I was discussing powers of 2 and 5 is how often they've shown up in a random mathematical thing I've been reading or investigating myself, and thus how often they will show up in an episode. Like, when you're not trying to find stuff about them, but they show up with importance anyway. Very frequently, evens and multiples of 2 have some importance in some random aspect of math. Occasionally, powers of 5 and multiples of 5 do. And the 3 evens and multiples of 3 are just a little more on the frequent end. And yeah, I'm not sure why someone thought base 11 is a good idea. I think they hopefully were just suggesting that it could be a good example of like one day's lesson of class is, what if we counted in base 11 instead? Here's what that would mean. And the benefit would be if you mostly use base 10 already, you're only adding one symbol. However, usually due to the divisibility, the most common example given is base 12, because you get more divisibility, more in common with base 10. You're adding 2 symbols, but it's worth it for the easiness. You also, for free, get clock analogies if you're, willing to look for ways to express it in terms of clocks. In fact, when I first started grade -1, I thought base 12 was probably the best. And it was only after finding a lot more data and researching all of their stuff, including their times tables and stuff like that, that I concluded that base 6 is neater. And it really is neater is the main pattern, I would say, which makes that stuff easier, because they have other traits in common, like that totient function. How many numbers under them are co-prime to them? 6 or 12 have exactly 1/3 of the numbers less than them co-prime to them. So there's some random traits that base 6 and 12 are very similar. They both are made up of 2s and 3s, multiplicatively. But base 6 is just neater. And it's to everyone who complains that you're going to need to write an extra digit occasionally in your base 6 representations instead of your base 12 to write the same number. Well, big deal. You're going to have a real sore hand from all the times that you need to write down 20,000 of a thing. It's like, how often do we use that massive size of number? You don't write down an 8-digit number that often. So, big deal that they're going to be 9 digits now. I think your hand can deal with it. Someone's saying repeated decimal notation reminded them of continued fraction notation. And the rational numbers can be written with a finite number of digits, and the algebraic irrationals can be written as repeating digits. And yeah, some of them, when you're writing continued fraction notation, even a few of the algebraic irrationals are, it's not all of them that have a recurring periodic string necessarily that will work like that, but all of the numbers that are of the form the square root of an integer at least. So I made a continued fraction episode that has a lot of that stuff for people who didn't see. But the idea is that something like square root of 2, part of why I say fractions are superior to decimals is that, well, if I say something like 1/3, the fraction is neater than the decimal. And, in any base we pick, some fractions are going to be neater than their decimal counterpart. The decimal needs an infinite repeating thing. But at least it's repeating. But if I say square root of 2, any basic base I count in, of like base 2, base 6, base 12, whatever, it's not going to repeat. It's going to have an infinite non-repeating string. A decimal is really bad at trying to explain square root of 2. In fact, a decimal arguably never explains it because there's no real pattern in saying what's going on at the, 1/infinitieth digit in a casual way of the series it's approaching. So it's almost like decimals only give you approximations of a square root up to an arbitrarily close accuracy, but never fully there. Because there's no way to write a string with a line over it or whatever to say it in an equation. the only way to really say what's going on with square root of 2, you'd think, would be, oh, square root of 2, or x squared equals 2, and it's the positive solution, or stuff like that. But when you bust out infinite fractions, and some people are like, what? You can't make a fraction of infinite. It's like, why not? You were already making the decimal infinite. You let decimals be infinite. Let's let the fractions try. Well, the fractions have a wider domain of ones that are periodic. And like this comment mentioned, which the comment mostly is phrasing similar to the stuff I was saying, is, and that was on the main combo class channel episode, but it is a fun one, the continued fraction episode. And the continued fractions are like a step ahead of decimals. Decimals, it's like, okay, if I'm a rational number, a continued fraction version of it, which you can make this version that looks like the infinite ones but is finite, this thing called a continued fraction will be finite length for any rational. And for decimal, it's sometimes finite, sometimes infinite. And so it's already worse at that stage than the next stage. For irrationals, decimal will automatically be non-repeating, no pattern. For certain irrationals, the continued fraction has a period. And I have one of them on my wall back there. So let me see. Let me get this bigger camera up for a moment. So back here on the wall, do you see that back there where it says square root of 2 equals 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, etc. forever. Now, that has its denominators. We have a 1 at the start, we could say, and then all the denominators are 2. So it's almost like this alternate universe version of how some decimals look like 0.1222222. So if I can take the number 1/6 and write its decimal as 0.16 with a line over the 6, you're like, I could do a notation like that to explain square root of 2, which couldn't do that with the decimal using a continued fraction. It's infinite, but big deal. Decimals were infinite just trying to write 1/3. So you can write it. There's a notation. It's like brackets, and then you have 1, and then you have a semicolon because the 1 was the whole number part. So it's like 1 semicolon, and then you put all the repeating denominators that we can put a line over. So, and that's just 2 repeating. So there are some ways that there's some similarities between decimals going 0.16 with a line over it to try and make a fraction, and how fractions can do a similar looking thing to make certain irrational numbers. So, and don't worry, it's not just my base 10 bias. Decimals are extra bad in the base 10 system. But even if I get people to switch to base 6 someday, fractions are still going to be better. So, while I have my face big, I'm going to look at the comments in a clearer form because I can see them up here on the screen without it being in the way. And yeah, you got some cool ones. And the continued fraction for pi, that one there is the simple continued fraction where all the numerators are 1. Another cool thing about continued fractions is that the simple continued fractions for certain types of irrational number, when you truncate them at certain points, provide the best possible, closest for a given denominator size, best possible approximation of irrational numbers. So, for example, with the pi continued fraction, if I cut it off at certain points and have this little translation I do with it, I get 22/7, 355 over 113, and all of those fractions that approximate pi. So I love continued fractions. They're cool. They might even get a sequel episode someday. The ones that are going to get sequel episodes first, though, are going to be hyper 11s, because, and 3-evens. There might be a, 27 more reasons why Threeven should be in the dictionary type episode, but maybe not 27, maybe 9 more reasons Threeven should be in the dictionary, but, or 6, that's a Threeven even, but there will be a episode that's a sequel to all of my talks and an episode I made once about what I call hyper 11s, the generalized rep units, or numbers that in a certain base are only contain the digit 1. And in fact, those Mersenne primes we bumped paths with on this stream earlier, those are the binary hyper 11 primes. Mersenne numbers in general can be called binary hyper 11s, and the primes turn out to be really important. Well, there's this extra cool thing about them that I want to make an episode about that are called the Catalan Mersenne numbers, but no need to look them up. I'll explain it in a fun way. A lot of the topics, I don't mind telling you folks about in advance, because I feel like some of them, if you try and look it up, you'll sort of feel like you hit a brick wall if you don't like studying text, which I do, but not everyone does. And one of my goals is to take topics that sort of look like a brick wall of text or mathematical expressions and like find a fun way to make an episode about them. There's plenty of quotes that I agree with that are about how sometimes the hardest skill and the sign of a deepest understanding of something can be the ability to explain something in a simple, catchy way that gives someone a simple gut feeling for it and doesn't take that many words. That's like the end game, the hardest thing to do with a field. First, you learn how to explain all the equations, and then you're like, how can I explain this to someone who doesn't even know what the equations mean? And someone's mentioning Taylor series and Maclaurin series. We haven't done those much yet, but maybe we'll do Taylor series in a Desmos stream sometime, because we can actually look at, for example, series that get close to looking like a sine wave without actually being a sine wave, just by using a bunch of factorials and stuff. So we'll do that on a Desmos stream sometime, where I have the graphs up. And by the way, to one of the commenters who I remember commented that you recognize parks around me, if anybody in the Bay Area does want to ever help me with combo class, feel free to email me at the contact link, which is combouniversity@gmail.com, because someone else already emailed me who I still need to get back to them. I will soon. But I am always looking for new people who are in the area if you want to help out in some way. And I'm going to shrink myself again so we can look at a few last numbers. And like I said, to anyone who likes my videos and wants to study more stuff on your own to build your brain, I recommend any of these articles that I had here during this stream, reading through them, and if you enjoy numbers, you'll probably end up getting sidetracked and clicking some stuff before you even get to the bottom of the first page. You'll probably have to keep going down a little rabbit hole back, down a little rabbit hole back, and so on. But this one's another fun one that I kind of skimmed past. The first one was called List of Numbers versus List of Types of Numbers. So I feel like Wikipedia could maybe find a way to merge these two pages. Like, I feel like you could definitely get confused and think you had seen all of the articles that were along these lines when you'd just seen one of these two. But this one is more of a list of numbers. They're like, these are the numbers. Then they go into some that they call interesting. And interesting to note, I was, mildly dissing 5 in comparison to 3 here. Well, what do you know? 5 is the first missing positive integer. 5 is the first, according to this sector of Wikipedia. There's other places on Wikipedia they use the word significant to describe 5, so this isn't necessarily their overall opinion, but according to whoever wrote this bit, 5 is the first insignificant positive integer. So, and then 7 is the next one. Now, sorry to the lovers of 5 and 7, they are a little overrated apart from being primes. Now, here you get just like traits about numbers. Those are fun. And you get families of numbers. And you get They really need to merge this article with this article. I feel like this is just confusing. There's a little overlap, but it's not all overlap. So I don't know. Read through both of them. Maybe one of you should edit this. In any case, shout out to whoever does edit Wikipedia episodes. Whoever does that are awesome people for society. So genuinely, they are super cool. I love Wikipedia. It's probably like the only website I like more than YouTube. So yeah, tons of good numbers. We're going to spend more time on individual ones of these pages at some point. Like this one could be, its own whole stream, apart from the fact that some of these will have their own episodes. But I also recommend it as personal reading if you're ever bored and don't know what to read. Also, if you want to read books, let me make a few recommendations while we're on the topic, which the ones I have right here are probably the same ones I recommended not too long ago. But since this was all about number theory, these are 3 particularly good number theory books. And I don't mean these are like textbooks that teach you up to this level of number theory like a college would. But I mean, these are fun books to read that also will give you a lot of facts. I recommend The Book of Numbers by John Conway and Richard Guy. I also recommend, this one's a little lesser known, but it's a great number theory book, Recreations in the Theory of Numbers by Albert Byler. And I also recommend this one called Wonders of Numbers by Clifford Pickover, along with his other stuff. And there's a bunch of other ones I'll recommend in the future, but those 3 are specifically kind of number theory-esque, which is focused on these type of pages. And if you needed to define number theory, you could be like, well, usually, at least in its simplest form, it's about stuff like Pythagorean triples or Fermat's last theorem, stuff like which positive integers or integers in general or rational numbers, depending on the circumstance, which numbers of a given type, often even just the integers, fulfill the properties to some certain equation, which, although it has an equation form, also often has a fun like gut feeling form, such as like the twin prime conjecture is a big open question in number theory, which relates to, are there an infinite amount of primes 2 apart from each other? So number theory often has like an equation that you can write it as, but also a sort of cool sentence or 2 you can describe it as. Now, of course, that's not the only subset of math we'll do episodes about. There will be some geometry type episodes before too long as well. Among other things, I mean, at some point we'll go into like random fields. We'll do like, okay, it's not theory week. Okay, it's topology month. So, let me check one more time. I'm going to make this large again, and then check our comments, as well as stick my head out the window again to see if our rain died down or if that's still going. I believe it's safe. So this is mildly risky, but I'm not feeling any rain. So if any raindrops appear on the laptop while I'm out there, I'm definitely going to have to end the stream shortly. What we'll do is I'll check the chat now to answer any questions or thoughts. And then once I go outside for a brief little field trip visit, we will be ready for me to end the stream at any point. If it starts raining, I'm just going to end the stream. So I'll say for now, in case it ends randomly, to anyone who watched, love you all. Thank you so much. Make sure to check out the Discord and or Patreon and stuff. and of course the main channel, which is the combo class channel for my full episodes. And, or by full, I mean like my most well edited, put together episodes. So, checking our chat before we go outside for a moment. Someone's mentioning Conway talking about how he didn't like to be remembered mostly just for the game of life, and that is, you know, a little sad that a lot of people know him for that, but in the math community, I think a lot of people do know and respect him because he has a lot of different cool discoveries and a lot of great writings and such. And so hopefully somebody, one of his math friends, comforted him after that and reminded him of some of his other discoveries. And someone also mentioned the Wallace product, which is an infinite product, which is cool too. I showed that real briefly in a short once, but I didn't really explain it or anything. And there's, yeah, people can look up the Wallace product if they want to see an infinite product that can be a way to approximate pi. And by approximate, I mean if you extend it to its limit, b pi. So, we're going to do a little field trip, but first, as I go switch locations, I'm going to switch us to just the background. And now I'm still there. Now we're just on the background. And I'm going to go outside for the end of our stream. And like I said, if it starts raining or anything, I'm just going to end the stream at that point because I'll have to eradicate inwards. But hopefully it won't rain and we can spend a final 10 minutes out there. So, I'm also not going to bring the charger, so it's going to be a limited amount of time. So, one moment as we switch zones. And there's going to be one part of the combo classroom that I can't show. I'll explain that when we're there. Ah, it feels fresh out. Now, it's not raining on me at the moment, but there's trees over the desk. So, hopefully it doesn't get windy enough that a bunch of rain just falls from the trees all over this. I also had to haphazardly put a tarp on my grandfather clock. And the desk is getting quite rained on as well already. So we're just going to be out here for a minute. And there's part of the classroom I'm not going to show you. It's because it's a big surprise that will be more interesting to see in the grade -2 combo class intro coming on the main channel in a few days, sometime on Sunday or Tuesday-ish. Probably Sunday or Monday-ish. And so I'm not showing that direction of the classroom because there's a surprise there. But on this direction, we can see that I had to put a big tarp over my grandfather clock. And my desk, I didn't have time to cover because this rain came kind of out of the blue. So the desk is taking its first raining. You guys can take bets on how long it would last. Maybe we will end up losing one leg at a time. Got all 4 legs for now. Now, heading over here for one moment to setting this on my desk, we can see that here I have written grade -2 as part of a scene for that intro episode that's mostly filmed. And I don't know if this was the rain or the squirrels, but they ate a lot of birdseed. That's crazy. Or maybe the birds. I filled this with birdseed yesterday. Now, the first time I did that The squirrels knocked off the bottom of this thing, and it all fell on the ground. And there's still a bunch on the ground, because I was like, maybe I'll leave it on the ground and the squirrels will eat that, and then the birds have this. But now the weird thing is the bottom's on it, but it's empty. That's weird. I guess the birds and squirrels just ate a lot of bird seed. Okay, hopefully the birds got enough. And we also... Wait, what was I looking at here? The squirrels, yeah. Have some very fun cameos in the intro episode. Keep an eye out for a squirrel that caused a little ruckus in a fun way. Squirrel had an actual little action appearance. So we'll try and draw the squirrels closer. Now that I have the bird seed, I'll start putting out nuts, and we'll lure them into staying more and more. Now it's getting a little windy, so it's probably going to start sprinkling droplets, and yes, it is on the computer. So we're going to wrap up the stream now. Thank you all for joining me and for all of the comments. Make sure to be tuned for some random episodes on this channel coming in the next couple days still. Like, I filmed one about a little fun paradox of sorts down by a nature area not too far from me. And it's really windy, so I'll probably still put it out, but warning, my shorter video about the paradox I'm going to be putting out in a day or two on this channel has a lot of wind noises, warning. But I need to bring a better mic when I go to the area by the ocean next time. So, in any case, the normal audio will be coming in the main Combo Class channel official intro episode, where we have a lot of cool surprises and fun in that. So, stay tuned for that. For example, do you think I got any more dice? Maybe I got some more dice. Also, make sure all of you have checked out that grade -1 finale episode. Not the final exam I dropped, but after that, the sort of documentary-like adventure I dropped on the main Combo Class channel. It's like 33 minutes, but it's a cool, big project. It means a lot to me. So at some point, watch through all of that. And grade -2 is going to be even more fun. I got so many topics that didn't fit in grade -1. I got to end this stream now, though, because this computer is going to get soaked the next time the rain comes back. So, thank you all. And love you all.